Hello, everybody. Thank you for coming out. Just want to make a note. If you came to this talk in Chicago, it's mostly the same. So unless you want to, probe me with questions afterward or whatever, you might want to go somewhere else or something. But anyway, my name is Zack Loebel-Begelman. I'm a senior software engineer on the data platform team at a company called Credit Karma, and we're here today to talk about Akka Streams for high-throughput data processing. Make sure you rate the app so I can get some feedback, and the next time I do this, I can hopefully do better. So anyway, what are we talking about today? First of all, who here is familiar with Akka Actors? Just show of hands. Cool, most everybody. Who here has written code using Akka Streams? Okay, still quite a few hands. But has anyone tried to solve a high-throughput problem using Akka Actors? A few people. So for those of you who raised your hand, this is for you. You get to hear about my pain doing that. So what are we talking about today? We'll start off talking about the data infrastructure at Credit Karma. We'll talk about how, as we scaled our data, we started running into problems. A little bit of an introduction to Akka Streams, some of the core concepts and how some of those things work. How Akka Streams saved my butt and made my life much better. And then a little bit of benchmarking, comparing Akka Streams to Akka Actors, finishing off with a few results and learnings. So without further ado, this is what the data infrastructure at Credit Karma looked like when I first started. Credit Karma, for those of you who don't know, is a financial assistant helping over 60 million American and Canadian people make financial progress. So when I first started at Credit Karma, this is what the data infrastructure looked like. We had just introduced Apache Kafka. And for those of you who don't know, Apache Kafka is a highly durable message queue. Provides at least once guarantees. It's very scalable. You can shove a lot of data through it very quickly. It's high throughput. So we started pushing JSON into Kafka, which is a semi-structured data format. Our analysts were comfortable using Vertica, a ACID-compliant relational data store, which likes big batch inserts. Also, because it's ACID compliant, it's very strictly structured. So we have JSON in Kafka, but we need to have these strict types guaranteed and pushed into Vertica. The other thing with Vertica, because it's a columnar store, it likes these big batch inserts. You don't want to insert one row at a time, it'll go really slowly. You want to do hundreds of thousands or even millions. So we need to batch up our inserts. The other thing, because of those at least once guarantees in Kafka, you get duplicates sometimes, right? If a message doesn't make it through, sometimes it gets written again and you get a duplicate. So we wanted to remove those duplicates. Those were the three constraints and the reason we built our data warehouse import. One of the applications we'll be talking about today, written in Scala using Akka. More on that shortly. The other application we're talking about, the analytics export service, came about when we partnered with a third party called Amplitude to provide us product metrics and client interactions with how people were using kind of our application and our website. Now, we never sent any financial data. It was always anonymized. We take security very seriously at Credit Karma. This was another Scala service using Akka Actors. And these are the two applications we're going to talk about today. Kind of how do we pull that data out of Amplitude, push it into Kafka, and then how do we get it from Kafka into Vertica? So this is really about our experience building the actor systems and ultimately switching to Akka Streams. So what about the scale of the data? Here we have megabytes per minute over the past 4 years. So these aren't gigantic numbers. It's not a Google or a Facebook necessarily, but it's still non-trivial. It's enough to where we needed something that we knew that could scale. So you'll note in 2014, we had about 162 megabytes per minute. And you can see we kind of doubled over the next few years. But what I thought was really cool is it's actually not strictly doubling. It's actually an exponential growth. We didn't necessarily expect that. We expected it to about double. But either way, we're glad we prepared for that. That's why we chose to use Scala, because we wanted something on the JVM where we could have kind of threads spun up as necessary, but also Akka. Now, most of you know, Akka Actors is a different way to think about concurrent programming, leveraging the actor model. Right? No locks, no synchronization necessarily. The actors are kind of like a heavyweight function, where your message is your inputs to that function. And it actually scales very well. Because all of the mutable state is contained within an actor, it scales easily to other boxes or even other threads. Send a message, actor does a thing. You can send that message over TCP if you want to. You can have it clustered. These are some of the reasons we actually opted to use Akka Actors. Also, Akka Streams wasn't available at the time, but it's a push-based model. Send a message, do a thing, change your behavior, create more actors, whatever that might be. So we chose Akka Actors because we wanted to scale with our data, and we knew it would be easy, hopefully. The other thing that's nice about Akka Actors, you can send it to a single actor, or you could send it to a router of actors. You don't necessarily need to know. You're just sending this message. It could be handled by any number of actors on the same box or on a different box. So what's the application that we built using Akka Actors here? Our data warehouse import. So if you recall, we had 3 constraints. We want our batch inserts into Vertica. We need to deduplicate messages out of Kafka. We also need to convert our semi-structured JSON into a more strictly structured, it was actually TSV, is what was preferred. So this is what we wound up creating. We had a single extractor for every topic in Kafka, for every table in Vertica, and that extractor would be responsible for creating 3 other actors: a reader to get the message out of Kafka, a deduplicator to make sure that we only ever sent unique items. We did this using a sliding hash map, amortizing the deletes, linked hash map, I guess. So what would happen is the extractor would push a message to the reader, who would read a message from Kafka, then push a message to the deduplicator, to then push a message to the processor. It would actually make sure all the fields were there, the types were correct, and that would convert it to TSV. That would then push that message back to the extractor, which would write to disk, uploading to Vertica when relevant, and then pushing another message to the reader to start the whole process over again. So there's something to note here. We only ever had 1 message in flight per extractor. So per table in Vertica and topic in Kafka, we only ever had 1 message, or message from Kafka, I should say, in flight. So this actor system worked really well for a while. It worked so well, we decided, hey, we've got this other amplitude use case coming up, this analytics export. Why don't we use it to build that? So what did we have to do for this one? Well, we have a coordinator. Amplitude only makes this data available once an hour. So it's this tarred gzipped file that we pull from Amplitude once an hour. We untar it, unzip it, and then we have a bunch of files that we want to do some transformations to, and then send it over the network into our ingest server. So we wound up having a router of these transformer workers to take it from the kind of Amplitude format and convert it into our internal format. We then had a Kafka import worker that would actually make the network call to our ingest server, which at the time would receive a batch of messages over HTTP. It would write them to disk, and then once it had written all of them to disk, it would actually respond. We had a separate agent that sat on the box that would actually consume those messages from disk and push them into Kafka. But that's the high level of what this is doing. We built it, we were super excited about it, we shipped it, and immediately we ran into problems. So the first issue we ran into was data missing. This is the exception that we actually saw after shipping it. So we were using Spray at the time. We were using the host level connector, I think it's called, where you have pretty much a connection pool. You ask Spray for a connection, then you use that connection to make your actual outbound network call. So we were seeing futures timeout asking Spray for the connection. That meant the connection pool was effectively saturated, and we weren't able to get a new connection within 30 seconds. So we figured, okay, this probably isn't good. It's not a big deal, but we're starting to have work queue up in memory, and the futures are timing out, and the data's getting dropped. That's fine. Should be an easy fix, right? 30 seconds. What if we just crank that up to, like, I don't know, 30 minutes? That should be fine. What's the worst that could happen? Out of memory is the worst that could happen. So while we were missing data before, now I'm getting paged because our application is crashing. So we didn't really fix the root cause here. We're still waiting on network, except now instead of those futures timing out and throwing an exception, the data disappearing, the data is piling up in memory. Eventually, enough data piles up in memory to where the whole application falls over. So we really weren't controlling the rate of work well. Again, easy fix, right? Just crank up the heap space. So we did that, but we knew it probably wouldn't work forever. So we decided to take kind of a closer look at the architecture of what exactly it was that we were doing. So we'd get these gzipped tarred files from Amplitude, we'd unzip them, we'd read them from disk, and as we read them from disk, we would actually do this in-memory transformation that was pretty fast. Then we have a little bit of a slower network call, still decently fast, but then we have a really slow write to disk before responding. So what we were literally seeing is work piling up, right? The ingest server's going slow, The import workers are going a little faster, but still, it's nothing as fast as those in-memory transformations. So you're just having work pile up at each step until the application falls over and I get paged, which I don't want. So we knew this was going to be a problem, but we weren't sure what the fix was. It was actually around that time that we looked at our data warehouse import, and we noticed there was actually a similar paradigm occurring. You have a pretty fast network read from Kafka. For recent messages, it's really just kept in memory, so you're mostly just bound by network. You still have a pretty fast in-memory transformation, right? We're deduplicating, we're transforming JSON to TSV, and then what a surprise, we're writing to disk. Vertica also is likely writing to disk when we upload it. So it wasn't before long before we started running into problems there too. So here we actually have a graph of throughput. This is reads from Kafka, and that green line is our rate of ingest. So 750,000 is our magic number. So if we're not above that line, we are falling behind, and we will never catch up. So what changed to cause this weird behavior? Obviously, it does really well at the beginning, comes crashing down, and then we even have a 20-minute period where we don't do any work. So this is no good. We're also using swap space. Data's not getting loaded into Vertica, so people are starting to chase me down. I'm trying to figure out what exactly changed, what's different here. So we had a new schema or topic in Kafka come online. Previously, our largest schema was about 8,000 events per minute. This new schema was more on the order of 80,000 events per minute, 10x growth. So apparently that was enough to make the whole system fall over. I'm unsure what's going on. There's this halting behavior. We're using swap space, which is never good for a JVM application. I just know people are chasing me down. I'm still getting paged about the other application. And I figured there has to be a better way. So Akka Streams had actually just gone GA around this time, and we decided, hey, let's take a look at this. Maybe this can fix our problems. So what is Akka Streams exactly? While with Actors, it's all a push-based model, send a message, Akka Streams introduces this concept of backpressure, or a pull-based model. It's still Actors under the covers, but it's a much friendlier API that's really optimized for throughput. It's also a very modular API that's very composable. So what will happen is it actually starts at the end. You have your final subscriber, or a sink, in Akka Streams parlance, that will send a request for data or demand. And that'll go all the way through the chain until you get to the beginning, at which point the data is actually sent along. So this concept of backpressure was formalized in the Reactive Streams manifesto, or Reactive Streams specification, sorry. And this is actually, Akka Streams implements that. You can get everything as a Reactive Streams subscriber or publisher. These are still all non-blocking asynchronous signals, because they're actors under the covers. But again, it's kind of a high-level API optimized for high throughput. I do want to make sure to mention, Akka Streams is limited to a single box. There's no remote or clustering that's available. Just because these are all actor messages, it's possible one of those messages when getting sent over TCP could get lost. And if that message gets lost, it's possible your stream could deadlock. So you have to be constrained within a single box. That's the big gotcha that it's important to note. So what are some of the core concepts that you'll find in Akka Streams? Everything starts off with a source. This is kind of where your data comes from. I also want to note everything is a graph stage. So you have these source stages, which has one output into the stream, because its input is something external to the stream. Something like a file, or it could be a sequence, or an iterator, it could even be an actor reference. There's a bunch of these APIs built in that provide backpressure for you. No custom code necessary. So once you have your data in the stream, you have an output that's exposed, you have a flow. This flow is a way to potentially transform or change your data, something like a map or a filter. We'll look at some of those soon, but it's actually a lot of things that you'll find in the Scala Collections API. It has one input and one output, and it's just a way to do some sort of transformation. It's a way to connect different things. The other thing that's really nice is the API on these flows is really the inlets and the outputs and the types. So you can actually have these composite flows, where maybe I want to expose 3 flows that do a variety of things as a single flow. That's all possible, just because the API is kind of what's your inlet and what's your outlet and the types. So once you have your data transformed or changed, it goes to a sink, kind of the final resting place of the data, something with 1 input and 0 outputs, because the output is going to be something external to the stream. Again, something like a file. It could be a sequence, or again, sending to an actor. And once you have all your inputs and your outputs connected, you have a runnable graph. That's your blueprint. That's the work that will be done. It's still the blueprint, it's freely shareable, but no work is done until you actually call run on that blueprint or that runnable graph. It's at that point when kind of all the resources are allocated, things are materialized. Materialization here is that you can have certain stages that materialize something. So something like that's a sequence, it would materialize a future for a sequence when run is actually called. And that's where all of those resources are allocated. You'll also note anytime there's something that you provide to a stream, it's going to be a function. That's because that function will be invoked every time run is called. So let's actually take a look at some code. If you recall, for our data warehouse import, we were doing some deduplication and processing. So I want to show just kind of how easy it is to write some unit tests that allow me to focus on my business logic and just plug in values. So we have our deduplicator. That's a flow that takes a string, it outputs a string, and it doesn't materialize any value. That's that not used. We had to write a custom graph stage for the deduplicator just because that functionality didn't exist. For the processor, we're effectively doing a map. I've written it as flow from function, but normally you could actually just call map on a stream that you had. And you'll note we're just calling process schema, where we provide the bytes. It takes the string, and it provides an option for a string. So what does the composite look like? We can say deduplicated via processed. And now we actually still have a flow, but instead it's a string that returns an option of a string. And that's, like I said, that composite flow where we've now taken two and put them together. But now let's plug in a few values to write our test. So first off, let's drop the values that we removed using a filter and just get. We'll then create some data that we want to push in. We use a sequence here as our source. And then we just send it to a sync to a sequence. And we say, OK, keep the materialized value. You can see we have a runnable graph that will materialize a future of sequence of strings. That's the other thing I really like about Akka Streams personally is you get type safety. You know at compile time if your program is correct. Otherwise, it won't compile. Because the types on all the inputs and the outputs are known and wired up, you actually know you have type safety, something that isn't available today with Akka Actors. So we also still need to create an actor system and then a materializer using that actor system, and then we call run. That actor materializer is an implicit value provided to the run function. We get our future, we wait for it to resolve, and then we just kind of make sure the result's correct. Right? So I can still test my business logic, but I can plug in other values for our sinks or our source just to make sure that my flows are correct. I can focus on what it is that I want to test instead of wiring up all those actors, making sure the case classes are correct, and things of that source. So what are some of the built-in APIs that you get? Some of the built-in sources, things like an actor reference, a queue, you can use a sequence, you can have an iterator, or you can use a path. There's built-in functionality to read and write from the file system. All of that you get out of the box using backpressure all the way through. No custom code necessary. Similarly, for our syncs, we have things like head and head option. These should be starting to look familiar for those of you who have used the Scala Collections API, which I assume is everybody here. But things like last, for each, reduce and fold, and you can materialize a queue that you can have something read from or write to on either end if you need to kind of communicate with the outside world. Similarly, with a lot of the built-in processing stages, you see some familiar functions, grouped, sliding, take while, things like that. And for any of those, for a lot of functions, there's another version that will contain it within, where you can provide a timeout. So if you're creating a batch or something like that, and you don't get enough elements within 5 minutes or whatever number you prefer, it will just produce the values at that point. Just because it's a potentially infinite stream or potentially bounded, who knows? But if you don't get enough in time, just produce the values. Same thing with some of the converters. You have an input stream, output stream, and even a Java 8 stream. If you want to plug in with external things as sources or sinks in your stream, you can use those functions. So let's look back at our warehouse import and what exactly we were doing and what it looks like with streams instead. So like I mentioned before, we had created a simplified version of backpressure. We created our own little mini Akka streams without realizing it, just because Kafka is potentially unbounded. We had to. I also want to make sure to call out, as is best practice, or is my understanding with Akka, is you want to wrap every message to your actors in a case class. So, right, extractor would send a case class to the reader, which would get stuff from Kafka, put that in a case class, send it to a deduplicator, wrap that stuff in a case class, send it along to a processor, wrap it in a case class, send it to an extractor. So we're pretty much making 5 case classes for every message we get from Kafka. That's important later. We'll come back to it. But what does it look like when we take away some of those actors and we replace it with streams? Well, it's much simpler and less diagrams on my chart. You just have the stream. Right? You now have an extractor that instead spins up a stream, and that stream does all the work for you. So we now have an extractor creating a stream for each topic in Kafka to each table in Vertica. It's simpler to reason about, and we no longer need to be concerned about the type safety, because we know it's correct, otherwise it wouldn't compile. So what does the code look like? So you'll see we have a runnable graph of not used. That's because we don't materialize anything. We start off, as I said, we have a function to get our iterator from Kafka. We also create our message parser. That's where we predefine, hey, here's the schema you're using of the types to look for. We then send it through our deduplicator we saw earlier, at which point we pretty much do a map to process it. That's turning that JSON into a TSV. And then we send it to an actor we had used previously, our schema file writer. This is a trait that I believe has been deprecated at this point, but it was really useful for us. But the concept is you can have an actor subscriber or publisher where it's a trait you can pull in, and it will provide backpressure if you're converting an existing actor system. But I believe that's not so much supported anymore, and you'll have to use custom graph stages at this point, which are still pretty easy to write. But either way, we have backpressure all the way through. We have a stream, but we don't actually have a stream yet. We have a runnable graph. And you'll note in our receive block below, because we're actually still within an actor, that extractor, as you might recall, it's not until we get that start extraction message when we actually call run. And that's the point where, okay, the stream's actually created, resources are allocated, and work begins. So that's where kind of the magic happens, if you will. So it wound up actually being more performant. It's now type safe, and we know everything that's going on. It's easier to reason about. So what about our data warehouse, or our analytics export? What does that look like? Well, we have a few different routers here that we're able to just completely get rid of and replace the whole thing with a stream, similarly with before. While our unzip thing created multiple files, we wind up creating a stream per file. So this is kind of our high-level diagram. What does the code look like? This one's a little more complicated than the previous one. So we start off, for each file that we have, we're going to first read from disk. Like I had said, that functionality is built into Akka Streams. So we're able to use our kind of from path method on the file IO object. That gives us raw bytes, or I think it's a byte string. So at that point, you have to frame it, because we just have a bunch of bytes coming in, and we want to split it by new lines. So that's what that framing thing does, is it's once it sees a new line, it says, okay, this is a single event. We then turn it into a UTF-8 string, and that's when we use something called map async. So there's a few methods within, built into Akka Streams that you can run asynchronously, map being one of them. So what map async does is similar to how we had a router of actors before, we now can parallelize our map, right? So instead of an A to a B, we now have an A to a future of B, but we can run it in parallel, providing a desired level of parallelism to that function. So what will happen is, once all those slots are full, and you have all of your maps going, it will backpressure. It'll stop asking for new work until one of those spots opens up. So here we did that to actually turn things into a J object, to parse it as JSON. We then do a filter to drop the schemas we don't care about. We turn it into our internal type that we're familiar with. We then run map async again, where we do our internal transformation. This is something we want to parallelize. It's a little more expensive. We then group it up into the batch size we want for our network call, and then we make our network call. That's that last map async. And this is where we were running into problems before, because we were waiting, or we had work piling up, and we only had so many connections. Now we can just explicitly limit it. We provide this parallelism input to this function, and once all those slots are full, all those connections are in use, we just backpressure. We just wait. Once a slot opens up, we can actually pull another one off the queue and then send it along. So that's where we make our network call, and then we send it off to our onComplete sync. The idea of that sync is that if the stream completes successfully, it just sends you a try, pretty much. And so we were using Akka persistence, I think, for the checkpointing. Cool, we're done, file complete, move on. Again, easier to reason about, provides type safety. We know if we're correct, we don't need to wire up all those routers, we don't need to manage those ourselves. It's all kind of done for you in a very friendly API. So it was more performant. Let's take a look at before. Here we have heap utilization in gigs. You can see we have to reallocate several times. This is why I kept getting paged and had to keep upping the numbers. But we're using about 28 gigs. And then if you look at it after, it's using about a third as much, and much more predictable, consistent all the way throughout. I think this was, yeah, something on the order of 12. But either way, we can now run other things on that box. We have consistent heap utilization, and I'm not getting paged anymore, so I'm very happy about that. What about our warehouse import, though? This graph was still haunting me. We had this halting behavior, and it clearly wasn't working for us. So this is our before. What does our after look like? It takes a little bit to get up to our previous 9 million number, but we stay consistently between 8 and 11 million, leaving our previous 750 number in the dust. Our ingest rates, as you saw before, have continued to go up, so luckily we switched to streams so we could support it. But this thing's humming along, no problem, running at capacity, effectively. But I was still bothered by this halting, pausing behavior, right? This 20-minute period where we didn't even have anything occurring. It took a few benchmarking runs, but I did start to notice some trends, and I think I know what the issue was. Recall before I said we're making about 5 case classes for every message we got from Kafka? Well, I think that was a few too many, because if you take a look, we have garbage collection times shown here. Our before is at the top, and our after is at the bottom. I want to make sure everybody notices the before at the top is in seconds, and the after in the bottom is milliseconds. So we're talking several orders of magnitude of difference. You can see there's a few periods on there where we're literally spending more time doing garbage collection than we are doing actual work. Several 20 to 25-second pauses, and that's that halting behavior I was seeing. The other thing is, if you're using swap space and you're garbage collecting, that's going to take a very long time. That's the other thing that you want to make sure you don't ever do, just because you have to pull references from disk, very slow. At the bottom, we have 40 to 80 milliseconds. The application barely notices. Throughput is hardly hampered, and things are working much better. So throughput has improved. I can finally get some sleep. I'm not getting paged anymore. People aren't at my desk asking, hey, Zach, where's my data? So this was a big win for us. But it's not necessarily, there are some of you skeptics out there that might be thinking, okay, no. His code's probably super crappy. If I did it, it would be much, much better. So to those, I decided, okay, what if I change my hat? What if I say, okay, let's write some code where I focus on the business logic and do a apples-to-apples comparison of actors and streams. So that's what I did. I decided, okay, let's pretend I'm not Zach, a platform engineer at Credit Karma, but instead I work for the Wikipedia Safety Corporation. Due to changing political climates, we want to make sure Wikipedia is safe for eternity. So for those of you who don't know, first of all, thanks Wikipedia, but Wikipedia actually publishes a dump of their whole website, or all the data in the Wikipedia, twice a month. It's a pretty large, I think, bzipped file that once unzipped is about 60 gigabytes. So I decided, okay, I work for the Wikipedia Safety Corporation. I hear Akka Actors are cool, Akka Streams are also pretty cool. I don't know which one to use, so let's try comparing and contrasting. I want to focus on my core business logic, which is encrypting files from Wikipedia. So I wrote a XML parser. Well, I didn't write one. I used the one in the JDK. But pretty much, we need to parse some XML. Wikipedia publishes it in this wiki markup language that we also needed to do some parsing, do some encryption. We did RSA encryption, and then we'll write it back to disk just to make sure it's all safe. So I wrote the business logic separately, and then I plugged them into very thin actors and streams, and decided to take a look. And so just to keep consistency, why don't we take a look at our speed distinctions here, right? So we have a slow read from disk. We have a pretty fast in-memory transformation, a little bit slower encryption because it's RSA, and then we have a pretty slow write to disk. So what did we do for this? We ran it in AWS. It was a 4-core box with 8 gigs of RAM, and I thought it'd be interesting to take a look at 3 different disk speeds. So we need to parse the XML from disk. I pre-downloaded the file. It's about 60 gigs. I want to make sure everybody notices it's a 60 gig file. We have 8 gigs of RAM, so 60 larger than 8, we'll get into trouble, potentially, hint, hint. We use the JDK built-in parser for XML, which is in the JavaX XML stream library, or package. I wrote a trivial wiki markup parser. Scala has built-in parsers, or it's easy to build a parser in Scala. RSA encryption built into the JDK. I used a file output stream for our actors, and because it's made sense, I used the Akka Streams file API, because I get backpressure, and it's all built into the stream. Why would I not? So the first test we ran was our kind of baseline test. Let's just read the stuff from disk, parse the XML, and write it back. The idea being, we shouldn't be able to go any faster than this base test. So it took us 16 minutes and 27 seconds. Great. OK, why don't we try it with actors? And I work at the Wikipedia Safety Corporation. I don't know any better, so can anyone guess what happened? Ran out of memory. Because again, 60 doesn't fit into 8, no backpressure, no nothing, and we're just slamming these actors. Eventually, we out of memory. But turns out there's this concept called a bounded mailbox. So you can define a size of your mailbox that's used for those actors, and if that mailbox is full, it will block until there's space in the mailbox. So once we use the bounded mailbox, we also used some routers just to make it interesting, the actor's finished. Took about 40 minutes and 27 seconds. Raw streams were actually slower. And I suspect there's a few things that happen here, but because there was no async boundaries in my stream, I believe it actually comprised it into a single stage, and it's still kind of slow. But either way, once we used map async, it was actually significantly faster. Faster. 28 minutes compared to 40 minutes. This is still a pretty big improvement. But it wasn't necessarily just about it going faster. There were some other results that I personally thought were interesting when we looked at the different disk speeds. So on this graph, lower is better, because this is runtime. And you can see we have 3 different disk speeds for the source: slow, medium, and fast. We have our baseline test, where we don't really do anything. We have streams using map async, raw streams, and then 2 different actor implementations using different routers, both using a balancing mailbox. So what I thought was really interesting on here is with streams, as our source disk got faster, the whole thing got faster. Pretty cool, makes sense, right? It's built for high throughput, reducing bottlenecks. We see the inverse with actors, actually, is that as our source gets faster, the whole thing actually gets slower. I suspect this is just because work's going a little faster, and it's not necessarily controlling the rate of work in any way. There's more overhead in terms of objects, and your guess is as good as mine, but either way, streams are built to reduce bottlenecks, and you really see that here, in that as there's more speed available to juice the system, the whole system goes faster. While with actors, the inverse appears to occur. So it wasn't necessarily just, though, about the performance. I had a few revelations as I was writing the code to do this. So everybody, don't try to read the code on the screen. I just want to illustrate a point. So first of all, right, when implementing the actors, obviously I had to spin up all those actors and point them at one another. But then I realized, I also needed to implement a parsing actor, and then I needed to implement a file writing actor, and then an encrypting actor. And then I realized, the system doesn't actually know when it's done, so I needed to figure out a completion message so that when all the messages had gotten there, we'd send that. And either way, it felt like a lot of boilerplate. I wanted to focus on my business logic. If I wanted to write boilerplate, I would just write Java. All right. So a lot of boilerplate, because we're just doing maps pretty much, right? And I had to make all these actors to do this. Meanwhile, with streams, much less lines of code. It's also a lot more readable and easy to understand about what's happening. So if we take a look at what's going on here, right? We start off, we have a XML file source. I did have to write a custom source to pull those messages from XML, but I had to do similarly for actors, so I thought it was fair to leave it out on both. And you'll also note this whole thing is a composite source. The types on these are sourced all the way through until we get to the end when we actually have our runnable graph. So we start off, right? We provide a file input stream to our source. We then parse the messages, which give us a try of wiki page. Here you can see in one I have a map async, and the other I have a plain old map. And then we remove the stuff that has failed, because we don't really care. We then try to do our encryption. Again, another just map or map async. And then we just kind of drop the stuff that failed, we turn it into a byte string, and write it to disk. So not only is this a more performant API, but I can wind up actually focusing on my business logic. Instead of trying to make sure all the types are correct, wiring up all the actors, I can just focus on the business logic of what I'm trying to do here, which is keep Wikipedia safe. But there were a few other things, right? So first of all, to make the actors work, we had to use a bounded mailbox. We also had to use routers just to make it interesting. It took several hours when I tried not using it, and I just didn't even bother putting the results on. And we also had to figure out a completion message. Meanwhile, I get all that stuff more or less for free using Akka Streams. And so a few of you might also say, no, you can juice the actors more if you do this or that. That's the conversation I keep having with my coworkers. But that's not really the point I'm trying to make here, is I could spend my whole life trying to tweak Akka. That's not what I'm paid to do necessarily. Because I want to focus on the business logic and leave the rest to potentially the experts or whomever wants to do that stuff. So that's my 2 cents there. Let's actually take a look at some of the performance metrics of those benchmarks. So we have GC times here. We have our baseline tests first, then we have our 2 stream implementations, and then our 2 actor implementations. The streams are sitting pretty at about 20 milliseconds of consistent GC pauses, and you can see they're all over the place for the actors. Kind of makes sense, you're making a lot more case classes, but again, right, much more consistent usage for the streams all the way throughout. Meanwhile, you have this high variance all over the place, which is likely not helping our throughput. You see similar trends with load. This is a 4-core box. So when you can see our actor tests going up to 20 to 25, that box is not having a good time. It's not going to scale a lot more. If we wanted to do more things with that implementation, it would likely fall over because it's already being pushed mostly to the limit. Meanwhile, with the streams, they're sitting mostly pretty, a little under 10 or at about 8, consistently more or less throughout. So you can see one of these will scale much better than the other. And you see similar trends with heap size. Heap doesn't even move with the streams. It's at about 750 megs. Meanwhile, actors, it's going all the way up, and that's where you see our allocation or our GC times, is because the heap's all over the place. Meanwhile, streams manages most of that for you, and it's just consistent the whole way through. So what were our learnings or takeaways here? Raw Akka actors are very powerful, but there's no backpressure. So you can really get into trouble when you're going from fast, especially when you're going from fast to slow. They're also not especially composable. You need to make sure the types are correct. You need to point them at one another. They are good for low latency. And if you need clustering, and frankly, if your data set is small and fits in memory, then use whatever you want. It doesn't necessarily matter. You probably won't run into an issue. Akka Streams, meanwhile, are optimized for high throughput. They're built still on top of Akka Actors, but it's built to reduce bottlenecks and done with a very friendly high-level API you can use, like I said, built to reduce bottlenecks. And if your data doesn't necessarily fit on a single box, you're likely going to have to use a source that will scale along with the needs of your data. Something like a Kafka consumer, or split the files yourself, or whatever it might be, you're likely going to have to partition that yourself. So don't be like me. Don't try to build a high throughput thing with an actor system. You'll just start building Akka Streams. The folks at Lightbend have done it for you. It's a very nice, very usable API that I enjoy working with. So thank you very much. Any questions?
Okay, thanks for the talk. But can you explain in more detail how did you connect Akka Streams to Kafka as a sink or as a source?
So yeah, I was using it as a source. In my specific example, we were just using the iterator from Kafka. At the time, I think, because reactive Kafka is a thing now that's managed by Akka. It's actually a pretty nice API also. But we were just using the raw iterator that Kafka provides. And because you can build a stream using just an iterator as your source, or source wrapping an iterator, I should say, we just used the iterator, and that worked for us at the time. There were some things that were missing in terms of committing offsets, but for our use case at the time, it worked. Does that answer your question?
Okay, thank you.
Cool. Anyone else?
Thanks for a very good example of Akka Streams implementation.
Sure.
The question, did you consider Kafka streams basically to implement the same topology?
So I did recently actually benchmark a few different tools. Unfortunately, I didn't get a chance to analyze Kafka streams. So if I was speaking, it would be mostly anecdotal. My understanding, I'm going to stay away from that one. I can't say that I tried it. For that specific use case at the time, we had an actor system already. And it seemed sensible to just convert all of those pieces. Also, I don't think Kafka streams even existed at the time. So no, we didn't really consider it.
Okay, thanks a lot.
Cool. Well, thanks for coming out, everybody.